Greetings, welcome to today's session on steering. So first what we will do is we'll quickly recap this the material on steering, and then we we'll solve one problem on steering. Okay, so let's get started. Alright, so these are the functions of a steering system. It should allow for regulating a vehicle along a desired course. So we should be able to provide control input to the vehicle for lateral movement, or for lateral motion, and it's a critical system that ensures proper handling of the vehicle. So let's take a look at some introduction. Main requirement was to steer the wheels to enable the vehicle to travel in an arc. So if you are to consider an arc with this point as a center with some radius r, and given the vehicle's length being L, initial design was to pivot the front axle so that we should be able to take turn. However, these kind of axles were not suitable for high speed. So, what ended up happening is something like Ackermann steering geometry came up. Here, as you can see, a trapezoid is made and the wheelbase length forms a triangle with the front axle. Okay, if we take these two arm lengths to be equal, which they are, this becomes a trapezoid, and this trapezoidal forebar is what becomes the Ackermann geometry. Okay, so if you were to take a turn about this particular point, which is in line with the rear axle, these two lines are perpendicular uh, to these wheels. Okay, so this trapezoidal geometry can be moved using various methods, such as rack and a tie rod from the trapezoid along with the steered axle. So let's quickly go through components of a steering system. There are two broad groups: worm type mechanisms and rack and pinion mechanisms. There are following components like steering wheel, steering column, steering mechanism or box, track rod, pitman arm, and tie rods, and steering arm. So let's go through these one by one. Okay, so first thing is a steering ratio. This is the ratio of angle through which the steering wheel is turned to the corresponding angular displacement of the steered wheels. So steering wheel is the wheel which is kept by the which is rotated by the driver to give steering input, and steered wheels are the wheels which respond to this input. For most cars, it is between 12:1 to 20:1. Uh, so this type of steering mechanism helps the driver to turn the loaded tire onto the road by providing some mechanical advantage. So this is the steering shaft and column. We have the steering wheel, we have a collapsible section, a flexible coupling, and since these two are misaligned, there is an universal joint, and finally a a steering rack or a gearbox. So the idea behind collapsible steering column is that it prevents right, a collapsible section that helps prevent forces generated in a collision being transferred to the driver. That means in case of a collision, this column would collapse and driver would not uh, hit the steering wheel. So it will prevent some forces from being transferred. Okay, so if you are to classify the steering system, there is manual assist and there is power assist. So in manual assist, there is rack and pinion or steering box based on worm gear. Here we are leveraging the mechanical advantage. In the power assist system, external energy is fed through another system so that it becomes easier for the driver to turn the wheels. Now, if we look at power assist, there are various types such as hydraulic power assist, where the hydraulic system in the car is utilized, or there is electro-hydraulic, where both electrical and hydraulic systems are used, or electric power assist. Manual assist steering systems include pitman arm type, with it's a linkage type along with worm gear based system. So it provides reduced steering effort but less feedback to the driver on change in wheel conditions. They are typically used with rigid axles or heavy vehicles. And the rack and pinion type is the simpler one, which is lighter and cheaper. It generally gives more feedback to the driver and typically uses an independent suspension, which is used in light vehicles. Okay, so let's take a look at a pitman arm type steering. So we have this stub axle which is connected. Here we have the tie rod which connects this track rod to the tire, forming linkage, and there are two joints here. So this track rod is rigidly connected to a pitman arm which is rotated in here with the steering gearbox. As the driver rotates the steering, the input goes to the steering box and it appropriately rotates the pitman arm. So this is usually found in heavy road vehicles as trucks and buses. It has a steering box with high steering ratio, so it gives better mechanical advantage and hence it can be used in heavy vehicles. Although nowadays we do have power assist available on the heavy vehicles. So let's go inside and take a look at the worm and sector steering box. The worm gear is meshed with the sector gear, which is mounted on the same shaft as the pitman arm. Okay, so as the steering shaft rotates, this worm gear rotates and this sector gear would also rotate, rotating the pitman arm. Now, one benefit of such kind of worm gear arrangement is that worm gear arrangements are non-back drivable. So by that what we mean is, if we were to provide any input, so if we were to give any input to the steering wheel, then the worm gear would rotate and sector gear would transfer it to rotation of pitman arm. However, the tire rod forces will not be able to back drive the steering wheel, which is desirable in our case. Okay, so let's look at worm gear and roller steering box. Here there is a roller that is meshed with the worm. Okay, the roller roller is mounted on roller bearing and is held captive at one end of the cross shaft. When the worm gear turns, the roller twists the cross shaft and thus rotating the pitman arm. And the worm gear can be shaped like an hourglass to provide a variable steering ratio, higher towards the center and lower towards the end. So, in a sense, it becomes adaptive to the steering angle desired. Then there is a recirculating ball steering. Okay, so here we have the pitman arm, which is connected again to the sector gear, right, which is connected to a nut, and this nut is driven by these recirculating balls, which connects to the steering shaft. So here a ball nut is meshed with the worm gear through ball bearings, and the rotation of steering wheel would result in motion of the ball nut, the sector gear. So these balls serve to reduce friction between the worm gear and the ball nut, and they also reduce wear since the balls recirculate instead of having one ball in the previous one. This is a common type of steering box for a pitman arm system. It has less free play, or it has the or slacks the previous designs. Okay, slack than the previous design. Then we have a cam and lever arrangement. Okay, here worm gear is known as the cam, and lever studs travel on the profile of the worm gear when the steering wheel is rotated. So the rotation of steering wheel would result in motion of this lever arm. So the lever stud rotates the cross shaft and thus the pitman arm. It's a very compact design. Then we have a rack and pinion system where there is a rack on the track rod and a pinion gear, which when rotated will have which when rotated would cause the steering motion. Okay, so the steering column can rotate the pinion gear, and this pinion gear's rotation would result in the rack traveling left or right with respect to this point. So this kind of system is more compact, it has less components, and it provides a more direct path to the wheels. So here there is something called a C factor. It is the distance traveled by the rack in millimeters when the steering wheel is rotated by 360. So if the rack speed is VR, that is given by omega s into C factor divided by 2000 pi. Okay, and thus the torque to obtain the force Fr in Newton meters is given by this expression. Now let's take a look at power steering. So if you were to read this plot, there is force at the end of steering drop arm. This is what the driver would provide, and force at the steering wheel. Force at the steering wheel is what the driver would provide, and this is the force at the end of the arm. So if you were to see, as we increase the ratio 15:1, 20:1, and 25:1, right? This is what the manual steering, how the manual steering would behave. But if there is power assist, you can see that significantly less force is required to generate higher forces. For example, at 600 Newton of force at the drop arm, you would need around 180 or 190 Newton of force at the steering wheel, whereas here you would only require around 50. Right? So power steering uses hydraulic fluid pressure to assist the steering movement. This system would require a reservoir, pump, hoses, uh, control valve, pressure relief valve, and a hydraulic cylinder. So let's take a look at a powered rack and pinion system. Okay, we have things like pump driver belt which drives the pump. There is reservoir and the pressure hoses. There is a control valve, a power cylinder, along with the steering gear and steering column. Here, the power cylinder acts directly on the rack bar within the steering rack housing. The fluid reservoir can be on the top of the belt driven hydraulic pump. Right. So the control valve is on the end of the steering column inside the rack housing. So the fluid is fed to the power cylinder via valves and hoses, and the valve is controlled based on the yeah. So the control valve operates with the direction of movement when the column is rotated, and the control valve directs fluid flow to the correct side of power cylinder piston. The piston moves and assists the steering rack in the movement. So there are many type of pumps. So this kind of pump can be used in a power steering system. They are functionally the same. Their job is to supply fluid under pressure for the system to use, essentially provide energy to the system. Okay. So the most common type of pump used on power steering system is a vane type. It is shown like this. There is a vane bar. You can see that there are vanes, a vane body and a vane housing. Okay, to drive this system. So there is a belt which comes from the engine onto the pulley, which rotates this entire assembly of vanes and vane body inside the vane housing. So a vane type pump takes in fluid, compresses it, takes in fluid, and then it pressurizes the fluid and gives out the pressurized fluid on its as its output. So this is how a vane type pump operates. Right, there are inlets where fluid comes in. As you can see, this is a bigger chamber, and as this kind of rotation happens, it first expands and then it compresses. So vanes are something which are like plates. These plates moves inside and outside uh, into this into this vane body, which is like a slotted cylinder. As this rotates inside a elliptical shape, uh, the volume available keeps on changing. So as this volume expands, a suction is created, pulling fluid from the inlet. Right. So the size of cavity between the vanes as they rotate increases near the inlet, forming a low pressure region to draw fluid into the pump. And as we go closer and closer to outlet, the volume starts decreasing. As this volume decreases, it pressurizes the fluid and sends it out. Okay, so the fluid is at low pressure in the inlet pipes and at high pressure on the outlet pipes. Right. So for a hydraulic power system, a continuously running pump is needed, and this contributes to the consistent power loss into the system. All right. This kind of system will not work if there is any kind of engine failure. So An electrohydraulic system is where uh, it drives the hydraulic pump using an electric motor, but this results in two energy conversions, first from electrical to mechanical using the motor and mechanical to hydraulic. Now let's take a look at electric power steering. In an electric power steering, there is a assist function which provides, this assist is provided directly by an electric motor. It has improved fuel economy since the motor run only when the driver is steering the wheel, and it can work even when the engine is stalled by taking power from the battery. Okay, so here the steering feel and assist characteristics can be tuned easily, but it depends on vehicle battery for energy and prevents its application in heavy vehicles as of today. So now let's take a look at Ackermann steering geometry. If you were to consider CG at a point L1 from the front axle, which is denoted by AB, and total wheelbase is L, this length would be L2, right? Now, if we were to consider a turn about point O, which is say R1 away from the center of the rear axle, and R is the turning radius, then we would require the front two wheels to be rotated by delta I, which is the inner wheel with respect to the turn, and delta O with respect to the outer wheel. Okay, right. So these delta I and delta O angles are intercepted here. Okay, and W is the track width. So this is a trapezoidal mechanism where this arm's length is D, this arm's length is also D. This is the track width and this is the connecting arm. Okay. So we want to check, can this achieve Ackermann steering condition? Alright. So uh, alright, so let's look at lateral dynamics. We shall consider the bicycle model where two front wheels are combined as one and two rear wheels are combined as one. Okay. So there are two models. First is a kinematic model which is reasonable at low vehicle speeds and it assumes slip angle to be 0. And then there is dynamic model that considers forces acting along the lateral direction at the tire rod interface. Okay, so we'll take a look at these lateral dynamics models in detail. So this is the kinematic model, and here we are considering the bicycle model where we are merging the rear wheels as one single wheel and front wheels as one single wheel. So the steering angle for front and rear wheels are delta F and delta R. So this is a generic model where we can where we can consider both the wheels to be steering wheels, and then we can substitute delta r equals to 0 for the vehicles we are familiar with. Okay, so let me switch to handwritten notes which are much more detailed so that we can have discussion on the derivation in a better sense. Right. So, okay. So we are looking at a kinematic bicycle model which neglects the tire slip along the lateral direction. So if we were to consider this point O, about which we want to consider the rotation of the vehicle, and R to be the turning radius, where point C happens to be the center of gravity. Okay, here the length, here AB is the vehicle, delta F is the front wheel steering angle, delta R is the rear wheel steering angle, right? C is the center of gravity, XY is earth fixed coordinate system, L is the wheelbase, V is vehicle speed, psi is heading angle or yaw angle or orientation, and beta is side slip angle. Okay. So yaw rate would be V by R, where R is the turning radius, right? And we can write x dot and y dot uh, like this. Okay, so if you were to consider this to be the x direction and this to be the y direction, V is at the angle psi dot plus, sorry, V is at the angle psi plus beta. So if we were to take its components, x dot will become V cos phi plus beta, and y dot would become V sin phi plus theta. So this is equation 1. Now if we were to consider triangle OAC and triangle OBC, okay, and here we are just working with, okay, so let's look at triangle OAC. So sine by triangle OA and C. So we can take sine of this angle divided by LF, right, and sine of the angle at point A divided by the radius R. This gives another equation. Similarly, if we write for triangle OBC, it gives another equation, right? And if we take first and add first and second, we get this particular condition. Okay, so from here we can find out the radius of curvature solely based on tan delta F and tan delta R. Okay, so here in equation 3, if we can closely take a look at it, the radius of curvature R is written solely in terms of the vehicle's parameters and operating condition. For example, L is the vehicle parameter, that is the wheelbase, beta is vehicle's heading angle, and delta F and delta R are the steering angles of front and rear wheels respectively. Put the lights also and keep it silent. Okay. Alright, so now if we were to multiply equation 1 by LR and equation 2 by LF and then subtract them, we can get this condition. Okay, and if we are to if we can just rewrite this, tan beta is LR into tan delta F plus LF into tan delta R divided by L. Okay, so we can find out beta, our side slip angle, also in terms of the vehicle's parameters. And if we can solve this first equation with 3 and 4, we can get the system. Okay, so this will give us the kinematic model. Okay, now this kinematic model is fine to work with in the linear region of the Fy versus alpha curve, right? So at small angles, Fy is directly proportional to alpha, which is the slip angle, and Cy is the cornering stiffness. So this is applicable during uh, small angles, but if we were to take a look at dynamic model, so let's take a look at dynamic model. Let us consider that the case where front wheels are steered by an angle delta and small xy is the body fixed coordinate frame. So you can write the velocity vector v at vx and vx of t into I cap plus y dot of t into j cap. This is velocity vector at center of mass. Then we have FIF and FYR, which are the lateral forces at the front and rear tire rod interfaces respectively. Let us consider alpha F and alpha R to be the slip angle at front and rear wheels or front and rear tire rod interface. Then we can write the acceleration at the center of mass as v dot of t plus omega cross v of t, right? And omega is psi dot into k cap, where psi dot is the yaw rate. So we are dropping t for convenience, and if we take a look at a at center of mass, we'll get expression for ax as vx dot minus psi dot into y and ay as y double dot plus psi dot into vx. So now that we have acceleration, we can apply Newton's law, Newton's second law of motion, right? So here we can write m into acm equals to f of t. See, if we were to write the force F as vector fx of t and fy of t and take accelerations ax and ay from above, this is what we end up getting. Okay, so this is a nonlinear ODE because these two terms are multiplying here. So in other words, these governing equations for translation are as follows. Now the equation for motion of rotation about center of mass is I into omega plus omega cross I into omega, okay, which is equals to tau. So we are neglecting roll and pitch here. So tau is written as 0, 0 tau z. Okay. So this is the inertia matrix, right? And we are just writing the above equation as follows. So we end up getting izz into psi double dot of t equals to tau z of t. Okay. So combining translation and rotation, we get the equation of motion for dynamic bicycle model. Okay. If we assume constant longitudinal speed, Vx becomes constant. That means V dot equals to 0. Then the equation of motion along y direction uh, becomes this. So here this thing goes to 0, right? And so m into y double dot. Okay. Yeah. M into y double dot plus Vx into psi dot equals to Fyf plus Fyr, right? And Iz psi double dot Lf equals to Lf into Fy of t minus Lr into Fyr of t. So this is a linear bicycle model which has 2 degrees of freedom. For small slip angles, we can consider Fyf equals to 2 times C alpha f into alpha f. Why 2? Because there are 2 wheels in the front. Okay. So this is a tire model which we are working with for now. There are certainly more sophisticated tire models, like magic formula tire model, which you can find in vehicle dynamics course. It's also available on NPT. All right. So how do we obtain alpha f and alpha r? So if we take Vf as Vfx plus Vfy, okay, Vf is the speed in this, right? And if we consider small angles, delta minus alpha f, if we were to take this right triangle, delta minus alpha f can be approximated as Vfy by Vfx. So alpha f can be written as delta minus Vfy by Vfx. Okay. The velocity of at point A is Vf, which is Vcm plus omega cross Rf. Okay. So this term can be opened up. Vcm is Vxi plus V plus y dot into j, and omega cross Rf is psi dot k cross Lf into I. Okay, which is psi dot Lf k cross I, which is psi dot Lf j. So we can merge these terms and get an expression for Vf, right? So this is Vf. All right, so this is Vfx. This is Vfy, which we can substitute here and find delta f. Similarly, we can write the velocity at B and obtain an expression for alpha r considering small angles again. Okay, so we have obtained expressions for alpha f, alpha r. All right. Okay. Now we can come back to the dynamical equation. The equation of motion for translating along y-axis becomes something like this. So m into y double dot plus m into vx psi dot that is mass into acceleration term in y direction, equals to the lateral force generated by the tire, that is 2 into c alpha f plus 2 into c alpha r. So we are using tire model as f equals to c alpha into alpha. So now if we substitute alpha f and alpha r as we computed previously, we get an expression here, right? So if we were to uh, rewrite this expression, we get an expression for y double dot in terms of the in terms of input delta y dot, which can be written as vx into beta, and psi dot. Okay, so next expression is for rotation about the center of mass. Here also we substitute alpha f and alpha r and get another expression for psi double dot. Okay, so if psi dot is written as r, this becomes r dot. Okay, so T1 plus R1 would give you governing linear second order ordinary differential equations for a linear bicycle model. Alright, so I think this is what I wanted to yeah. So then let's take a look at representation in terms of side slip angle beta and yaw rate r. So note that tan beta is y dot by Vx, and for small angles tan beta can be approximated as beta, which is y dot by Vx. So considering this, we can write y dot as approximately equal to Vx into beta, and y double dot is approximately equals to Vx into beta dot. Remember that we have taken Vx as almost constant. Okay, so next is yaw rate, that is r, which is psi dot. So r dot will become psi double dot. Now we can take a look at first equation, uh, which can be written in terms of beta, which gives an expression for beta dot, and similarly we can get equation for r dot as well. So if you were to write this in a state space form, this is how it would look. Our states are beta and r. Our input is delta. So the steering angle is the input, which changes beta and r. Okay, change in beta and r, that is beta dot and r dot, can be evaluated in terms of input and previous state using this state space equation. Now if you were to take its determinant, okay, and if you were to look at its determinant, its characteristic equation will be of the form a naught into lambda square plus a1 in a1 lambda plus a2. Okay, so yeah, we are taking determinant of lambda I minus a. So this is the characteristic equation, which is of this particular form, where a naught is positive, this is also positive, and a2 is this particular term. There is a minus sign, that means depending upon the values of these parameters, a2 can be positive or negative, right? Since we know that the necessary and sufficient condition for this characteristic equation to have both of its root uh, can you please mute your microphone? Alright, yeah. So if you have to look at the characteristic equation, now we are slightly moving into systems theory and controls, but it's alright. So for stability of this particular system, A0, A1 and A2 have to be positive, right? So since A1 is 1, it's positive, A2 is a positive term, we are only concerned about, sorry, A1 is positive, we are only concerned about A2 as there is a minus sign. So if you simplify this, we obtain an equation something like this, where this is weight in the front, this is weight in the rear, this has to be positive, alright. So, if we take this, if you calculate this load on the front and the rear wheels, okay, by taking moment about A and taking moment about B, we can get condition for asymptotic stability written as follows. Okay, so this term in the bracket is defined as understeer gradient or coefficient. Okay, so if this kV is positive, we call it understeer. This is stability condition is satisfied for all the values of vehicle speed. If kV equals to 0, we call it neutral steer and it's also stable. But if it is negative, then we call it as an oversteer vehicle, and uh, this is the critical speed which is defined. So all right, so let me quickly go back to this portion. So we discussed these equations in detail. It's still yeah, so these are the expressions for kinematic model, and we can obtain side slip. We just discussed how exactly we just hello, yeah, so we just discussed how exactly this kinematic model is uh, calculated. Okay, then how can we calculate this side slip beta also? So now let's quickly look at wheel alignment. It's important set of design and maintenance parameters. These parameters have to be maintained at the near design values for maximizing the lives of the tire and the vehicle. So if your wheel alignment is wrong, it impacts cornering. Right. So if your wheel alignment is perfect, it allows the vehicle to travel in straight line without any steering input from the driver, and it also minimizes the tire wear. So there are various signs of vehicle wheel misalignment, like vehicle pulling to one side, uneven tire tread wear, or uncentered steering. So first such parameter is camber. Okay, so camber is the angle which the wheel makes with respect to the normal to the ground. Okay, so if uh, it's a positive camber if the top of the wheel leans away from the body, and it's negative camber if it leans into the body. Okay, if camber is out of adjustment, it will cause wear on the sides of the tire tread. Right, if it is too far negative, then the inner treads will wear more, or vice versa. If the camber is different from side to side, it may lead to pulling. Right, it will have asymmetric force on the in the lateral direction, right, leading to vehicle pulling. If it is out of adjustment, then you can say that some component is bent or worn out. Second term in wheel alignment is called caster. So in the steering wheel, in the steering system, this particular wheel is mounted at these 2 points, right, the upper ball joint and lower ball joint. So this forms an angle. So this dotted axis which goes through right, ball joint and the lower ball joint, uh, yeah, is the axis about which the wheel rotates to allow for steering motion. So because of this particular length, uh, it allows us to safely return. For example, if you were to rotate the steering wheel and if you have to leave it, it will come back to the original position. That is happening because of something called as self-aligning moment. Yes, Ron, do you have any question? Okay, okay. So uh, because of this distance, right, since there is change of axis and the contact point is different from this point of intersection of axis, this distance would help us in generating a moment called self-aligning moment, which comes into action the moment you release the steering wheel. Okay, so this is the angle made by steering axis with the vertical direction when viewed from the side. So a positive caster means steering axis leans towards the rear of the vehicle, and negative caster means it leans towards front of the vehicle. The image shown here corresponds to that of a, I think, negative, sorry, of a positive caster. So if caster is out of adjustment, it may lead to problem in tracking straight lines because, as I told you, it should the self-aligning moment should align the wheel in forward direction. But if there is something mismatch, then the left wheel and the right wheel get aligned differently, resulting in some kind of yaw motion. Right. If it is, yeah, as I was saying, if it is different from side to side, it may result in pulling. In case of a positive caster, the point of intersection of steering wheel with the ground is ahead of the uh, contact patch. Right, this creates self-aligning torque. A high caster angle improves straight line performance, but it also leads to higher steering effort or lower maneuverability. That means there is a trade-off associated with respect to caster angle between straight line performance and lateral performance. Then there is tow. If you were to look at the vehicle from above, this is what tow angle is. Okay, it is indicative of difference between the leading and trailing edge of the wheels from viewing above. Okay, so there is toe in where the front sections of two wheels are closer to each other than the rear sections. Okay, so this is an example of toe in. Toe out is opposite of this example where the rear sections of the two wheels are closer to each other than the front sections. Okay, excessive toe in or toe out will cause rapid wear of the tires due to scrubbing. Okay, because even if the vehicle is traveling in the straight line, the tire makes an angle, that is the toe angle, which results in uh, lateral force generation in either direction, which perhaps gets cancelled but would result in tire wear. Okay, so it influences tire wear, straight line behavior, and cornering characteristics. So, toe setting is essentially a trade off between better straight line performance provided by toe in and faster steering response provided by toe out. Toe also impacts the fuel efficiency. So if the toe angle is way more than what the manufacturer specifies, it results in this particular thing. Sorry, yeah, excessive toe results in uh, fuel consumption, higher fuel consumptions. Then next one is steering axis inclination. It is uh, the angle made by steering axis with the vertical direction when viewed from the front of the vehicle. Okay, it's also known as kingpin inclination on trucks and cars that have ball joints. Oh, sorry, that have kingpins instead of ball joints. So then there is notion of included angle. It is the angle between steering axis and wheel plane. So this is the wheel plane and this is the steering axis. So angle 3 is what included angle is. Okay, it will be more than SAI, that is steering axis inclination, in case of positive camber, and less than it than in case of negative camber. So if the included angle is not same for both sides, then some component such as steering knuckle is most likely bent. So this kind of things allows us to figure out what component in the steering system uh, is faulty and requires some uh, attention. So more likely it is, in other words, we can say that by looking at these wheel alignment parameters, we can figure out or we can diagnose what needs to be, what changes to be made so that the vehicle works in a better way. Then there is something called scrub radius. It is the distance between the point at which this steering, this axis and the plane of the vehicle, right? So this is the distance between the points of intersection of steering axis and the central wheel plane. It if it is positive, it is positive when the point of intersection of steering axis with the ground is closer to the center of the vehicle than that of the body patch. Otherwise, it is negative. Next thing is setback, where one front wheel is behind the other. So the presence of setback would result in uncentered steering wheel. Okay, if it is centered steering means the position of steering wheel is central when driving on a straight flat road. Usually, a tolerance of 0.25 inches is accepted here. Then there is something called thrust angle. It is the angle which makes uh, this thrust line makes, which is normal or which is perpendicular to the rear axis. So if your rear axis are misaligned with respect to the vehicle, this results into a thrust angle. Okay, it is the angle made by the rear wheels with center line of the vehicle when viewed from the top, and a non-zero thrust angle may lead to uncentered steering. So in this particular case, if you were to connect to uh, the bicycle model, delta R comes into play, which leads to uncentered steering. So there are some points which we can quickly go through. Proper wheel alignment is crucial to minimize wear of tire and other vehicle components. Symptoms of wheel misalignment, that is, uh, which are uneven or rapid tire wear, pulling or drifting from straight line, and uncentered steering wheel. Pulling of vehicle from side by side may be due to misalignment, and it can also occur due to unequal tire pressure, right? Because your tire radiuses would also get impacted with this, and of course with brakes. So what is wheel balancing? A tire is said to be out of balance when one section of it becomes heavier than the other. This would lead to increased vibration, and it is usually compensated by attaching a weight opposite to the heavier part, right? So that the weight is appropriately distributed. Then let's quickly take a look at steer-by-wire system. It will replace conventional mechanical components with electromechanical components. Here, the advantages are that there is reduction in mechanical component, it, and it improves ergonomics. Right, the human factors becomes better, and its limitation is that it would increase cost and can potentially have safety and reliability issues, which requires significant amount of work on it. So if you were to take a look at a tire which has worn out, there are various conditions which maps to different kind of causes and associated correction. So first there is rapid wear at shoulders, right, at these edges, right. So this is like underinflation or lack of rotation. If there is rapid wear at the center, that means overinflation or lack of rotation. Or if, and then there can be cracked treads, which is underinflation or excessive speed. And the correction for all these three is adjusting pressure to the specifications when tires are cool and rotate tires. So when tires are cool is a critical thing here. Then we have wear on the sides, right? This can be because of excessive camber, and we have to adjust the camber to the specifications. Then if we have feathered edges, it can cause because of incorrect toe. And if you have bald spots, that means it's unbalanced wheel. It is vibrating too much, causing localized damage repeatedly. Okay. Then if you have scalloped wear, there is lack of tire rotation or worn out, uh, or your suspension can be out of alignment. You have to rotate the tires, right? By that means change the position of tire so that tire wear is uniform. So yeah, if you are interested, you can find out this book, uh, Steering Handbook. It's published by Springer in 2017, and take a look at this. So, do you have any questions on steering? We can discuss now. If there are no questions, we can close the session. I'll wait for a couple of minutes. Alright, so if there are no further questions, I'll stop.
Hello?
Yes.
Hello?
Yes. Can you hear me?
Sir?
Yeah.
Yes, can you provide us the numerical problem on the kinematics analysis?
Yeah. See, I wanted to do something, but my iPad stopped working today for some reason. In the next session, I'll get redundant machines so that I can do problems on steering. Okay.
Okay, sir.
Yeah.
Actually, I have understood the theory, but the numerical problems which are given in the assignment are unable to solve by me.
Wait, hold on. Let me open up the uh, assignment. Okay.
Yes.
Wait, hold on.
It was a 10th week assignment.
Okay. Just quickly give me week 10, is it? Yes, analysis. I think braking analysis we discussed.
Yes, sir.
Unfortunately, I was unwell, so it took me time to upload. It's uploaded also now. Let's go to. Hey, there are. opening the quiz. So can you point out to a question if you remember?
Yeah, eighth one, sir.
Eighth one, right? Yeah. Consider four-wheeled vehicle with track of 1 meter and wheelbase of 2 meters. If the inner wheel is rotated by 20 degrees, the angle of rotation is okay. I think I can look into this notes and let me quickly check if this has Ackerman steering or not. Okay. Now that the answers are also given, I can quickly show you something. Okay. So this is the Ackerman steering condition. All right.
Yes.
Cot of delta outer minus cot delta inner equals to W by L. Okay. So let's see. You have track of 1 meter, that is W equals to 1. Wheelbase of 2, that is L equals to 2. Inner wheel is rotated by 20 degrees. So it has told you three things. W by L is 1 by 2. Inner wheel delta is 20 degrees. All you have to do is find out delta out. Right. So using this Ackerman steering condition, we can easily find out. Alright. So using this, you can solve that. Alright. Uh, so then now they are saying in problem 8, let the vehicle CG be exactly halfway between front and rear wheels. Okay, so L1 and L2 equals to 1. Then the corresponding turning radius is, so I think here we also figured out the turning radius, right, R, which is L2 square plus capital L square delta I delta O. So L is 2 meters, L2 is 1 meter, delta I is given as 20 degrees, delta out you can find out from here, so you can find radius as well. Okay. I think these are the two questions you had doubt in, right?
Okay.
Yeah. So you can also take a look at vehicle dynamics to figure out more details on lateral dynamics and all. Right. It's also a course on NPTEL. Okay. Any other questions? No, I think there is between factor and co-angle. I'm unable to understand. Can you repeat? There is a difference between caster angle and toe angle. Oh yeah, that's what you asked, right? Let's go back to caster angle and toe angle. So see, caster is something which you observe from. Let me come to the slide. Observe from the side. Okay, uh, and toe is something which you observe from the top. Okay, so the caster angle has, I mean, uh, yeah, it's this particular angle as shown here between the red and the green line, whereas toe is observed from the top and it's this way. Okay, yeah. Any other questions? So, how to download? Uh, See, I'm unable to capture your voice accurately. I don't know if it is my speaker's fault or the microphone. Can you type it in quickly? Oh, I do not know. I don't know any administrative things whatsoever, man. You should be able to get an email, or perhaps you can download it from the Swayam portal. Uh, I genuinely do not have any idea about these kind of things. I've never done an NPTL course as a student. Okay. I will ask relevant people to post where you will get an ID admit card. But I think somewhere here you should be able to look at it. See,
Sir,
I
admit card is emailed to us.
emailed. You can
Uh,
please check your email.
Sir, it will be provided 1 week before the exam.
Oh, okay. That. Thank you for the information. Uh, yeah. All right. Okay. So, are there any other questions?
No.
Yeah, I will upload it now only. I was unwell actually last week. Still, I somehow took the class. I'll upload this one immediately. Okay. I'll upload the other files also. All right. Thank you.
Thank you, sir.
Thank you.